Hey guys, all right, we are on example 16.7. So hopefully you guys have your PowerPoints open and you can follow along with me. All right, so we've got a situation that's similar to one that we had before, but this time we are dealing with electric field, not necessarily the electric force. Okay, so I think that's what we did on the last one that looked similar to this. For this one, I want you to try to remember that whenever there is a positive charge, the electric field lines are going away from it. Whenever there's a negative charge, like this one, those electric fields are going towards it. So this is saying for part A, what is the electric field due to these three charges at the fourth corner, or point P? Okay, so that's because this negative charge, the electric fields go towards it. This is a positive charge, so these, this electric field's going to push this one. And this is a positive charge right here. It's going to go at a diagonal. Okay? So these two, Q1 and Q3, are pretty simple as far as figuring because they're just in the straight X and straight Y. Q2 is a little bit different just because it's going at that diagonal, but like what we've already done in this section or this chapter is that we'll just do the Pythagorean and we'll find the angle, which is easy enough, and we'll be able to figure it all out. All right, so I'm going to go to this next slide so I can write some stuff down. All right, let's see here. I hope I have enough room for all of this. I'm going to kind of draw this again just so you guys can have a visual of it as we're going through. Okay, and then this one goes over here to this positive charge, and this is 6. Whoops. Okay, and then it goes up here to another positive charge, which is 4 microcoulombs. And it goes over here to this point right here. So it was a little bit off my drawing. Imagine that. Okay, so electric fields. I'm going to see if I can get a different color for this. All right, so the electric field, because of this one, is going to push like to the left. This point right here is going to point at it at like a diagonal. And then this one is going to pull towards it. Okay? So lots of vectors going on here. If you were going to add them all up, you could do that. You could kind of do something like, so this is Q1. This is, or no, sorry, I think this one is actually Q3. Yeah, this is Q3, this is Q1, and this is Q2. Which, it really doesn't matter what order you do it in. You could do it either way. So you could have like a vector going like this, and then a vector going like this, and then you're adding this straight down vector, and it's basically wanting you to figure out what the magnitude of that electric field is. Okay? So we're going to do that. So first, let's start with electric field 1. All right, so if you remember, based on the last video or two, whenever you figure the electric field, it is the force over Q. Well, if you take Coulomb's law, which is K Q1 Q2 over R squared divided by Q because of this right here, that's going to cancel one of those Q's out, one of those charges, and you're going to be left with this equation right here. Okay? So now let's just plug in some numbers. So we got 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. times the charge of 1, which is 4, times 10 to the negative 6th coulombs, divided by your R squared here. I didn't put squared there. So what is the R? And I didn't write this on this one, so I will. I'm going to write it with a different color, just because I have different colors, so why not? You know, got all this technology now, let's embrace it, right? All right, so what is the R? From the point, this point over here, to Q1. Well, it's 0.5. Okay, you got to square it. So whenever you do the math on that, you should get 1.44 times 10 to the 5th newtons per coulomb. All right, let's skip on over to electric field 3, just because it's a little bit easier than electric field 2. All right, so we're going to plug in our numbers. Q3 is -1 times 10 to the 6th coulombs over R, which is 0.2 meters in this case. Okay, and that's going to equal 2.25 times 10 to the 5th newtons per coulomb. And I'm going to get into the signs of everything here in a minute, okay? So just wait on all of that. All right, now electric field 2. So we got KQ2 over R squared. Plug in your numbers again. Q2 here is 6 times 10 to the negative 6th coulombs divided by your R. Now, how do you find the R? So that's this distance right here. Okay, so you got to do the Pythagorean here. Okay, so you've got your 0.5 meters squared plus 0.2 meters squared. Do the square root of that, and you should get 1.86 times 10 to the 5th Newton per coulombs. Okay, this is like A squared plus B squared equals C squared. Okay, this right here was the C. That's what we were finding, was the hypotenuse. Okay, so we've got all of our electric fields, but we've got to figure out what the magnitude of them are. So that means that we've got to do the sum of x's and the sum of y's. So let's do the sum of x. But before we do the sum of x, we've got to figure out like what this angle right here is. I don't know why that did that. Oh, because I hit the highlighter. We got to figure out what this angle is. But if we can figure out this angle, it's equivalent to that angle. So how can we find the angle? Well, we can just do inverse tangent of y over x. So we've got inverse tangent of 0.2 over 0.5, which gives you 21.8 degrees, I believe. Okay, so now, why did I do that? Because we got to do our sum of electric field in the x direction. So look at electric field 1. That's this one right here. Why is that electric field 1? Because that's coming from charge 1. Okay? Which direction is it going? It's going in the negative x direction. So negative E1. Now, what E2, does it have any x component here? Well, yeah, it's going at an angle, so it's got both x and y components. as far as cosine sine, what would I do there? Well, this is like the origin, and this is like your x-axis. So that angle is adjacent to the x-axis, so your cosine. So it's minus e2 cosine theta. Why is it minus? Well, think about in the x direction. If this was your coordinate system, that's going in the negative x there. Okay, and then E3 is going straight down here. So on the y, so it has no x component at all. That's all equal to 0. Okay? So now you really just need to plug in. So you've got negative 1.44 times 10 to the 5th newtons per coulomb minus 1.86 times 10 to the 5th newtons per coulomb. And you should get a total, oh wait, what did I do there? I need to add my cosine. This is cosine 21.8. Anyway, whenever you do that, you should get negative 3.17 times 10 to the 5th newtons per coulomb. That's just in the x direction. Okay, now we got to do the y direction. So go on over to the next slide with me. There we go. All right, so now we're going to do the sum of the y's. So think about this again. Does this E1 have any x component at all? Y component? No. Does E2 have a y component? Yes, but it's at an angle, and then it goes straight down for E3, so definitely a y component there. All right, so you would do like E, not the sum. Okay, I just said let's embrace the technology, and I'm taking that back now. Ugh. All right, so we've got E2, but let's think about, how about the picture right here? Is this, as far as y component is concerned, is it positive or negative? Well, it's positive. So you do it like this. And then this one is going straight down, so it's just minus. It's equal to 0. All right, so now plug in for that. So you've got 1.86 times 10 to the 5th sine 21.8 degrees minus 1.44, right? No. Wrong one. Trying to think of the E3. The E3 was 2.25. Okay. Times 10 to the 5th. And all of that is then equal to 0. All right. So you solve for that, and you should get negative 1.56 times 10 to the 5th newtons per coulomb. All right, so you've got, this is your electric field in the y direction. Your electric field in the x direction was this negative 3.17 times 10 to the 5th. So let's write that down. Okay, now we got to do the magnitude, so that means that we got to do the Pythagorean. Okay, and you should end up with 3.5 times 10 to the 5th newtons per coulomb. And your angle here should be y over x, so which is about 26 degrees. Now think about it. This is what I drew earlier. This is like E1, and then E2, and then E3, and then it would be like that. So this angle right here is the magnitude, the angle of that entire, that vector addition right there. So it's like south of west. Okay, and then I only have this space over here for part B. So it doesn't take up much space. So part B says, what is the acceleration of an electron that's located at point P? Assume that no forces other than the electric field are acting on it. Okay, so this is wanting you to figure out the acceleration. So let's write some equations down that we have. We know that force is equal to charge times the electric field. We know that acceleration is equal to force divided by mass, and that's actually what it's wanting us to find, is the acceleration. So if we plug in our charge times electric field here for force and divide it by mass, we can figure out what the acceleration of that electron is. So what is the charge of an electron? It's that elementary charge, so that's 1.6 times 10 to the negative 19 coulombs, times the electric field, which is the total electric field, so 3.5 times 10 to the fifth. And then you've got the mass, which is 9.11. And then you get 6.2 times 10 to the 16th meters per second squared. And that is